Good morning, students. Myself, Vijay Shankar from Electronics and Communication Engineering Department at Chibrol Engineering College. Today, we are going to discuss about the sampling theorem. Sampling theorem and how we can recover the original signal after the sampling of the original signal. Reconstruction and recovered, not the and, reconstruction or recover the original signal with Fs is equal to the sampling frequency is greater than or equal to 2 FM, where FM is the maximum frequency. Yesterday we already seen about what is a digital communication and what is analog communication. What is the first operation in the digital communication is nothing but the sampling. Okay, and we already seen the statement of the sampling theorem. That is, a continuous time signal can be completely represented in its samples and recovered is a recovered, my dear students. Recovered back if the sampling frequency Fs is greater than or equal to 2W, where W is the maximum frequency and Fs is a sampling frequency, or otherwise the another statement I already told that a signal which is a band limited to FM hertz can be completely recovered from its samples. If the samples are taken at the rate of Fs is greater than or equal to 2 FM. Okay. Let us assume the x of t, the signal, is a continuous time signal, and we take the impulse signal, impulse train. So individual impulse signals, you can add it, we can call it as an impulse train, and combining these two functions is x of t, and the sum of n is equal to minus infinite to infinite, delta of t minus n into ts, so modulated. Now this signal is continuous time signal is converted into the discrete time signal after the sampling. Okay. Now the delta of t. What is the delta of t? The impulse train of pulses. Delta of t is equal to sum of n is equal to minus infinite to infinite. Delta of t minus n into ts, where n is equal to 0, the value is x or delta of t at t is equal to 0. When n is equal to 1, the signal is delta t minus 1 into ts, the shifted version of one sample towards the right side with the ts and so on. Now, whatever the signal after the combining these two, the x of t and the delta of t, we can call it as a x delta of t. The sum of n is equal to minus infinite to infinite, delta of t minus n into ts, and now the t is also instantaneous amplitude of the signal at instant t is equal to ts. It becomes of x of n into ts. Okay. Now, before applying the Fourier transformation, first of all, you convert this x delta of t as a function in terms of the delta ts of t. The equation how we get that x delta of t is equal to Fs into sum of n is equal to minus infinite to infinite, x of f minus n into Fs. Okay, my dear student. Now again I will explain the last class in the Saturday class. I already explained this how we derive this expression after the continuous time signal is sampled with the impulse train, the discrete time signal, x delta of t is equal to sum of n is equal to minus infinite to infinite, delta of t minus n into ts, x of n into ts. Again, I will explain clearly. Please listen carefully, my dear students. So we got x delta of t is equal to sum of n is equal to minus infinite to infinite, delta of t minus n into ts into the original signal with samples n into ts. Okay, my dear students. Now, by using the trigonometric Fourier series, trigonometric Fourier series, I'm assuming a impulse train with a sampling frequency delta t s of t is equal to, here the three terms with a naught is a coefficient, an coefficient and bn coefficients. A naught plus sum of n is equal to 1 to infinite an cos n omega s into t plus sum of n is equal to 1 to infinite bn sin n omega s into t. Okay, my dear students. Now, the x delta of t, or x s of t, not the delta, it is a s, my dear students. X s of t is equal to x of t and the impulse train delta ts of t, sampling frequency. Okay, that is equal to, I'm taking it as x of t into this total function, my dear students. What is the value of x delta ts of t by using the formulas of a naught is equal to, what is a naught? 1 by ts integral minus ts by 2 the ts by 2. Okay, my dear students. Into the function x of t into dt. Okay, means that x of t is delta function only. A naught is equal to 1 by ts is at t is equal to 0. At t is equal to 0 value, my dear students. At t is equal to 0, the delta of t, x of t, nothing but it is a delta of t value is a 1. Okay, delta of t is a 1. So again, you can keep this as x of t. I am taking as a delta of t. The value is a 1 is equal to t1 by ts. So actually it is a naught. Now I am keeping here a naught by 2. Changing of the values, the a naught is a 2 by s. 2 by ts, not the 2 by s, 2 by ts. Okay, my dear students. Then an is equal to, now the an is equal to the 2 by ts integral ts by 2 ts by 2 delta of t cos n omega s into t dt. See here also the delta of t is equal to 1 at t is equal to 1 minus. So the value is at n is equal t is equal to 0, the cos 0 is a 0, not the cos 0 is a 0, cos 0 is a 1, and delta of t function is a 1, the 2 by ts, it is also 2 by ts. An is also 2 by ts. Now coming to the bn, bn is equal to 2 by ts, 2 by ts, the integral minus ts by 2, ts by 2, delta of t sine function, sine n omega s into t dt. Okay, my dear friends. So that is equal to 2 by ts. The value is again at t is equal to, the delta is a 1, but sine function is a 0. So bn is equal to 0. bn is equal to 0. Now delta ts of t, delta ts of t, delta ts of t is equal to a naught by 2. What is the a naught? We got 2 by ts, 2 by ts into 1 by 2. So because the a naught I substituted in the numerator into 2 by 1 by 2 plus sum of n is equal to 1 to infinite. What is the an? We got 2 by ts, 2 by ts cos n omega s into t plus the bn. What is the bn? We got 0. Sum of n is equal to 1 to infinite is 0 sine n omega s into t. So the third term is a 0, my dear students. Okay. Now the delta ts of t is equal to, here the 2 to get cancelled, becomes of 1 by ts plus sum of n is equal to 1 to infinite 2 by ts cos n omega s into t. We got the delta function now. Okay. So what is the formula here? The x delta of t is equal to x of t into x delta of t. Now we can substitute in this equation x delta of t or xx of t, not the delta, xs, sampling signal. Without confusion, you can see that it is a sample signal. See, it is not the delta, and here also not the delta. You can keep it as S, sampling signal. Okay, is equal to x of t into delta of t. What is the delta? Delta ts of t we got 1 by ts plus sum of n is equal to 1 to infinite 2 by ts cos n omega s into t. Okay, using the trigonometric Fourier series, we assuming the signal is delta ts of t a naught by 2 and an and bn, can find out the a naught, an, bn values and substitute in the x delta ts of t. Delta ts of t we got here, and this delta ts of t can substitute in this equation xs of t. The sample signal is multiplied with x of t and delta of t. Why I wrote there is a any signal is multiplied with the impulse signal will get the same signal only, because it is a sampled version. So it's a sampling signal x of t. Is one of the property of the impulse function. Okay, my dear students. In this equation, if I substituted, so x s of t, the sampled x of t signal, here x of t by ts, x of t by ts, the first term, and the second term, the sum of n is equal to 1 to infinite, 2 into x of t, or 2 by ts into x of t, cos n omega s into t. Okay, you got this function. Now expand this function. X s of t is equal to x of t by ts as the first term plus 2 into, my dear students. It's not the x of ts, okay. Plus expanding the function at n is equal to 1. Here see, when n is equal to 1, if I wrote 2 by ts x of t cos omega s into t. 2x of t by ts cos n is 1 omega s into t plus 2 by ts x of t cos 2 omega s into t plus 2 by ts x of t into cos 3 omega s into t, so on, my dear students. Okay. Now, if suppose the x of t, we know before applying the Fourier transformation, you have to know x of t, the Fourier transformation is x of omega, or the Fourier transformation is x of f. The shortcut notation, the actually is omega is nothing but 2 pi f, that is equal to x of f only. Okay. Now we can apply the Fourier transformation on both sides. X s of t is x s of f. I am taking the Fourier frequency, normal frequency, is equal to 1 by ts is a constant. What is x of t Fourier transformation? X of f plus 2 by ts. Now the Fourier transformation of x of t. Here I am taking the Fourier transformation of x of t cos omega s into t. Is all the term common with the 2 by ts plus Fourier transformation of x of t cos 2 omega s into t. Okay, plus so on. Now what is the Fourier transformation of x of t cos omega t? Now let us take that is x of t. How we can write this cos omega s into t e power j into omega s into t plus e power minus j omega s into t by 2, my dear students. Okay. The first one I am taking. Then x of t e power j omega s into t plus x of t e power minus j omega s into t whole divided here the x of t minus students. This is not the x of t. X of t whole divided by the 2. Okay. Now the Fourier transformation of this signal. Fourier transformation of the second. Now I am finding out the Fourier transformation of this signal, students. It is also the Fourier transformation. Now what is the formula? The x of omega is equal to actually. Okay, the Fourier transformation is equal to integral minus infinite to infinite. What is the signal here? X of t e power j omega s into t whole divided by 2. This is a total signal, my dear students. Into e power minus j omega t dt. Okay, plus for the second one, integral minus infinite to infinite x of t e power minus j omega s into t divided by 2. This is a signal for the second one into e power minus j omega t dt, because we are applying the Fourier transformation here. Okay, taking the first one only is equal to, now here the e power something and e power something is there, integral minus infinite to infinite x of t by 2. What is the e power here? The bases are the same. You can add powers. Take the common of minus j omega minus omega s into t dt plus the another integral also. We got the same thing, x of t by 2 e power minus j omega plus omega s, because it's both are minus into t dt. Now you can see this is the frequency shift property. According to the frequency shift property, the x of t into e power minus j omega s or the t minus beta, we will get x of omega minus beta by using the frequency shift property. Take the next one. By using frequency shift property, see here, actually instead of omega, here the omega minus omega s. 1 by 2 is a constant, x of t, this signal. Okay, that is equal to, you get 1 by 2 into x of omega minus omega s plus the second function is 1 by 2 into x of omega plus omega s. Okay, my dear students, we got the first Fourier transformation of x of t cos omega s into t. For the second one, the same thing, 2 will add here. Okay. For the next one, this is only the first one. The Fourier transformation of, what is the Fourier transformation of x of t by 2 cos 2 omega s of t. What is the second term I just want here? X of t cos 2 omega s by 2. That is equal to, using the same thing, 1 by 2 x of omega minus 2 omega s plus 1 by 2 x of omega plus omega s. Okay, and so on. Like that, you can add the two functions x of f. X s of f is equal to, what is the first term here? X of f by ts x of f by ts plus 2 by ts into this Fourier transformation. 2 by ts. What is a Fourier transformation? This one is a Fourier transformation. 1 by 2 x of now you can write it as in terms of f value is a f minus fs plus 1 by 2 into x of f minus fs, f plus minus fs plus, and here also see these are 2 by ts for these two terms. Again, if I am writing here also the 2 by ts, the second term is a 1 by 2 x of f minus f2fs, sorry, 2fs plus 1 by 2 into x of f plus 2fs. Okay, my dear friends. See, I wrote here that omega is angular frequency. It is a normal frequency. 2 pi f and the 2 pi f. The shortcut notation I wrote here is equal to, now here the 2 get cancelled, and here also the 2 is there, 2 get cancelled. The remaining terms s of f is equal to x of f by ts plus x of f minus fs plus x of f plus fs by ts plus, and here x of f minus 2fs plus x of f plus 2fs by ts plus so on. Okay, my dear friends. Now the x of xs of f is equal to, take all the terms since the 1 by ts is a common, 1 by ts. Now I am writing this as a sum of n is equal to minus infinite to infinite minus n infinite to infinite. When n is equal to 0, you will get this one, and n is equal to 1, and n is equal to 2, and so on, and n is equal to minus 1, minus 2, and so on. Okay, so x of, now I am writing it as a f minus n into fs. Okay, my dear students. So when n is equal to 0, we will get the x of f. When n is equal to 1, x of f minus fs by the ts. When n is equal to 2, x of f minus 2fs by ts. When n is equal to minus 1, minus 1 means minus into minus is a plus, x of f plus fs. Okay, you got it, my dear students? So 1 by ts is equal to, so finally therefore x of xs of f is equal to 1 by ts is a fs, sum of n is equal to minus infinite to infinite x of f minus n into fs. This is the equation we got the finally. Okay. Got it, my dear students? Xs of f is equal to fs, sum of n is equal to minus infinite to infinite x of f minus n into fs. It's a very, very important proof, the sampling theorem, the statement and the theorem, my dear students. So now you can, how we can recover the original signal by using the fs is greater than or equal to 2fm. Now we can go through that. Before that, whether we are getting the same answer or not, verify that one. See here, we got x delta of f is equal to fs into sum of n is equal to minus infinite to infinite x of f minus n into fs. Okay, my dear students. See the x of f is equal to 0 plus r minus fs plus r minus 2fs and so on. Here x of f is a Fourier transform of the original signal x of t. This equation shows that a process of uniformly sampling a continuous time signal results in a periodic spectrum with a period equal to the sampling frequency fs. Okay, my dear friends. See here the x of f, whatever we got, now we derive this expression from x delta of t is equal to sum of n is equal to minus infinite to infinite delta t minus n into ts x of n into ts by using the trigonometric Fourier series, and then after applying the Fourier transformation we got this x of or x delta of f is equal to, here x of f is the Fourier transform of the original signal x of t. This equation shows that the process of uniformly sampling a continuous time signal results in a periodic spectrum with the period to equal to the sample rate fs, nothing but the sampling frequency. The Fourier transform of the signal x of t results x of f minus n into fs, that is where f is equal to 0 plus or minus fs plus or minus 2fs plus or minus 3fs. Thus, the same spectrum f of x of f appears at f is equal to 0, at f is equal to plus or minus fs, and f is equal to plus or minus 2fs, and etc. This means that a periodic spectrum with period equal to fs is generated in frequency domain because of sampling x of t in the time domain. You know, the periodic function means repeated the regular interval. Suppose the signal is like this, minus fs to fs, and again it is repeated the same thing. The periodic signal is a periodic signal with the same period. Fs is a time period. Okay, my dear students. So thus the same spectrum x of f appears at f is equal to 0, f is equal to plus or minus fs, f is equal to plus or minus 2fs, etc. This means that a periodic spectrum with a period equal to fs is generated in the frequency domain because of sampling x of t in the time domain. Otherwise, if x of t would not have been sampled, then there would not be only one spectrum x of f around f is equal to 0. Okay, my dear student. Because of the sampling only, there is a periodic signal. It is repeated at the plus or minus 2fs and plus or minus fs and plus or minus 3fs. Otherwise, if it is not sampled, the x of t signal would not have been sampled. The signal x of t would not have been sampled, then there would be only one spectrum x of f around f is equal to 0. All right, my dear students. Next thing, x delta of f is equal to fs x of f plus or minus fs into so on, expanding the function. So finally, we are writing the same thing. The fs into x of f plus n is equal to 1 to infinite, my dear students, and not equal to 0. See, the same equation what we have, we get in the expression here. They're writing that fs into x of f minus n into fs. Let us, I will explain here. What we got, x delta of f is equal to fs into sum of n is equal to minus infinite to infinite x of f minus n into fs. So now when n is equal to 0, fs into n is equal to 0, we'll get the x of f1, x of f plus sum of the remaining functions n is equal to minus infinite to infinite and not equal to 0. In this range, n not equal to 0. This is n is equal to 0, my dear students. Again, it is a fs into x of f minus n into fs. Okay, this is the equation here. We got. So x delta of f is equal to fs into x of f plus sum of n is equal to minus infinite to infinite, but it is not n equal to 0, n not equal to 0. Fs into x of f minus n into fs. That sampling frequency you can recover with fs is greater than or equal to 2fm. Before that, you can see here, this expression shows that every term in the sum is the same spectrum at a multiple of samples fs. The equation can be written as x delta of f is equal to fs into x of f and sum of n is equal to minus infinite to infinite and not equal to 0 to the infinite fs x f of f minus n into fs. In this equation, the first term represents the spectrum that would have been obtained without sampling fs into x of f. And the rest of terms under summation represents the spectrum repeating at multiple frequencies of sampling frequency fs. It could not be the sampled means the first term only will get fs into x of f. Okay, my dear friends. The second term saying that the rest terms under the summation represent the spectrums repeating at multiple frequencies of sampling frequency fs. By the definition of the Fourier transformation, we know that x of omega is equal to integral minus infinite to infinite x of t power minus j omega t. And the Fourier transformation of x delta of t is equal to the sum of n is equal to minus infinite to infinite x of n into ts e power minus j into t. Frequency will get the n into ts, the t value, by f n into ts, as a t represented as n into ts. Okay. The above equation gives a Fourier transformation of the discrete time signal, hence it is also called as a discrete Fourier transform. Discrete Fourier transform. Let us consider the signal x of t is strictly band limited with no frequency components higher than the omega hertz. What is the omega here? Omega is nothing but maximum frequency. And having no frequency components higher than the omega hertz, the Fourier transform x of x of t has the properties the magnitude of x of f is equal to 0 for the frequency is greater than or equal to omega. Understood, my dear students? And the spectrum of such signal is known as the figure we are showing, the 1.2a. 1.2a. Let us assume the spectrum like this from minus omega to the omega, because the frequency omega is a frequency, higher frequency. It is not allowed the high frequencies. The spectrum of such signal is shown in that one. The shape of the spectrum is just arbitrary and is taken because it is convenient for the explanation, my students. Why I take this function as a rectangular function from minus omega to the omega, or minus fm to f plus fm. Let the sampling frequency be exactly equal to twice the maximum frequency. Twice the maximum frequency. Fs is equal to 2 omega or 2 fm. Here the omega is the maximum frequency in the x of t. This equation shows that x of f will be reproduced at f is equal to 0, f is equal to plus fs and the minus fs. So f is equal to plus 2fs and the minus 2fs, etc. Since Fs is equal to 2 omega, Fs minus omega is equal to omega, because of omega will get here, it is a 2 omega, or Fs plus omega is equal to 3 omega. Now it is increases like this periodically. Fs plus omega and Fs minus omega, and Fs plus omega is equal to 3 omega here. Fs minus omega is equal to the omega in this function here. Okay, my dear student. It is repeated, we'll get a signal, the spectrum of band limited of x of t, or the spectrum of sampled version of the x of t. Okay, so before that, you can see, before that, I will explain how we can recover the same signal what we are showing here. What we are showing this signal with a band limited signal, Fs is greater than or equal to 2 FM. Here they are showing that is a FM is Fs is greater than or equal to 2 omega. Nothing is difference, my dear students. Some textbooks are using the omega as a maximum frequency, and some textbooks are using the maximum frequency is FM. Whatever it is, the same, my dear students. That is, I am taking the same signal. What we are x of f at x is equal to 0 and minus omega and plus omega. Omega I am representing as a minus FM and plus FM. Okay, my dear students. I will explain the whiteboard. Let us take here a spectrum like this is x of f with the maximum frequency, the minus FM and the plus FM, and the 0 here as x of 0. Okay, this is the spectrum I am taking, and remaining here the 0 values, and these also the 0. Now the first case, if I am taking the first case, case 1 is Fs is greater than 2 FM. What is the definition saying that in the sampling frequency? A signal which is band limited to a signal, you see here, a signal which is band limited to the FM hertz. FM hertz can be completely recovered from its samples if the samples are taken at the rate of, if the samples is taken at the rate of 2 Fs is greater than or equal to 2 FM. Understood, my dear? So this is the definition of the, or the definition, the statement of the sampling theorem. Okay. Now I am taking the first case is a greater than. The sampling frequency Fs is greater than the 2 FM. Okay, assume. So to derive this, F is hertzes only. Suppose assume Fs is equal to the sampling frequency, let 15 kilohertz. Okay, my dear students, 15 kilohertz. Fs sampling frequency is greater than 2 FM. Greater than the 2 FM is a maximum frequency. Let I am taking here as a spectrum. Spectrum is minus 5 and 0 plus 5. Minus 5 and 0 plus 5. The sampling frequency, the distance here, the sampling frequency, it is at n is equal to 0, my dear students. But n is equal to 1, for n is equal to 1, we'll get the another sampling frequency here, it is repeated at the n is equal to 1. Nothing but it is a 15 hertz. Okay, the sampling frequency. 15. 15 means before that here see the 0 minus 5 and 0 plus 5. For the 5 here it is a 10. Subtraction of the minus 5 here, the 10, and adding of the 5 here, it is a 20. Okay, my dear students. So at n is equal to 1 greater than the 2 FM as per the frequency. And coming to here, so Fs now it is also shifted in the periodic function of the same signal. Now you see at n is equal to minus 1. N is equal to minus 1. Okay. Now when n is equal to minus 1 means x of f minus plus value you will get here. Plus value. And this fs is greater than the 2fm. So minus n is equal to, here also it is a 15. Difference is a 15 only. Minus 15 hertz here. Fs sampling at n is equal to 0, 0. It is a 15 samples kilohertz and here the minus 15. So minus 15, the before the value is a difference of 10. Is a minus 10 and the minus 15 before the value, the less value is a minus 20. Now you can see after the sampling, when n is equal to 0, we have only the fs into x of f, this value. After adding this function fs into x of f minus n into fs, when n is equal to 1, it is shifted the sample with the 15 kilohertz. See the 15 kilohertz, how it is a 15 into the x of f minus n is equal to 1. What is the fs here? The 15. X of f minus 15. These are totally the x of f. It is shifted with the samples, 15 samples, means at the origin. If suppose n is equal to minus 1, what is n is equal to minus 1? F plus 1. What is the frequency we are taking here? The 15 samples. So f plus 15. So towards the left side is shifted the total signal with the 15 samples. Okay, at the center here. Following, my dear students. So now observe these three, even if it is repeated again. What is the next one we'll get here? 25 and 30 and 35. Okay, but n is equal to 2. And n is equal to minus 2 is also, we'll get minus 25, minus 30 and minus 35. Is that minus 30 we'll get? Minus 30 and 2 into 15 and 2 into 15 and again this is so on. Okay, when n is equal to 0, n is equal to 3, n is equal to 4 and so on. Now here we are saying it is a low pass filter. What is a low pass filter characteristics? Ideal characteristics, we are saying it is a ideal characteristics. And practical characteristics is like this. Even if we are taking the practical characteristics to filter this signal after the sampling, the original signal is this one. After sampling, we got at n is equal to minus 1 and n is equal to plus 1 and n is equal to plus 2 and n is equal to minus 1. But by using the low pass filter, it does not allow the high frequency values, nothing but the greater than the 2 FM. By using the low pass filter, either it's ideal characteristics or practical characteristics. The practical characteristics, see here, like this, we'll get the practical characteristics. So higher frequency is not allowed, n is equal to 1, and the lower frequency, here it is also higher frequency, it is not allowed. Only in between of this only it is allowed. It is recovered the original signal what we have. minus phi, 0, and the phi value. Okay. We can call it as it's a God band. We can call it as a God band. GAUD, God band is FH minus FN. Higher frequency minus the lower frequency. What is a higher frequency here? If suppose this is a minus phi, we can take is a minus FM, and plus phi is a plus FM here, and this is a FS, the sampling frequency, because it's a 15 hertz minus FS, it is one. And this point, what is this point here? FS minus FM, FS minus FM, and this point is FS plus FM, and here this point is a minus FS plus FM, and this one is a minus FS minus FM. Okay, my dear students, and the gap between this, the gap between here, let us see, is the gap between this one, God band, means there is a gap in between of the two samples, FM to the FS minus FM. Okay, higher frequency, what is the upper cutoff frequency of the FS minus FM? Okay, and what is the lower cutoff frequency? It is a plus FM. Plus, not the plus minus, a plus FM. It is a minus FM. Minus plus FM. So that is the equation of the FS minus 2 FM. The band is FS minus 2 FM. Practical low pass filter is used to recover the original signal. Practical low pass filter is used here to recover the original signal, and reconstructed the X of F by the low pass filter. F is greater than 2 FM. F is greater than the 2 FM, my dear students. And the second condition is there, we have the second condition, FS is equal to 2 FM. Now we are taking the first case is the FS is greater than 2 FM. The second condition is FS equal to 2 FM. Also we can recover the original signal either by using the practical low pass filter or the ideal low pass filter. See here, both the practical and the ideal low pass filter using, we can recover the original signal, which is nothing but the FS is greater than or equal, greater than or not equal to, greater than the 2 FM. Okay, my dear students. Now I am taking the FS is equal to 2 FM. Second case, FS is equal to 2 FM. The same original signal you can take, original signal minus FM plus FM. Okay. Now the case 2. Case 2 is the FS is equal to 2 FM, equal to condition only. So the signal represented now at the same point, 0, minus FM, plus FM, and the second one is starts at the FM itself only. The sampling frequency FS here, FS. Okay, the 0 value. Now, in the right hand side, the periodic signal again, that is a minus FS. Okay, minus FS is started from the minus FM only, minus FM. Okay, now you can see the frequency. Here it is the FM, and this range is also the FM. So FM plus FM here. Is the range is FM only, here also the FM only. Okay, the 2 FM, the total is the FM is a 2 FM, equal condition. Okay, but here, when observe from this, the FM here, and from this, there is a greater than the FM value actually. Greater than the FM value, the band, whatever we have, greater than the 2 FM. Understood? Understood. So now it is equal to the 2 FM. The previous case, what we are taking, it is a greater than, in the present it is equal to FM only, at the point of FM itself. Understood? Suppose if I am taking the sampling frequency, now the sampling frequency is 10, 0, 5, 10 and the 15. Here the 0 and the 5, the sampling frequency is 10 kilohertz, and is a 15, and 0 minus 5. Now the sampling frequency at n is equal to minus 1, n is equal to 0, n is equal to 1, minus 5 means here the minus 10, minus 15. Okay, my dear students. Now it satisfies the Fs is equal to 2 into Fm. 2 into Fm is a 5 only. 2 into 5. It is a 10. Okay, the sampling frequency. But the sampling frequency previous case is a 50 kilohertz, 50 hertz. 50 kilohertz is actually it's a kilohertz only, the kilohertz we can take. Is the Fs is greater than, not the greater than, Fs is equal to, what is the value here? 5 only. 5 into 2 into 5 is a 10. Fs is a 10 actually, but where we got the Fs here, the 15 is a greater than the 10. 15 is a greater than the 10. Now here Fs is the 10 only, so equal to 10. So Fs is equal to 2 FM. In the previous case, Fs is equal to 15. It is a greater than the 10 actually. The frequency what we have, the maximum frequency. What is the maximum frequency when I assume here 5 is the maximum frequency. In the previous case is also the 5 is the maximum frequency. But the sampling frequency I taken, it is a plus 15. Means according to this equation, the sampling frequency is greater than the 2 FM. Greater than the 2 FM. Now the case is Fs is equal to 2 FM. Now here, what we have to use to recover the original signal from minus 5 to the 5. Suppose if I use the ideal characteristics, exactly that minus 5 to the 5 will get. Suppose if I am using practical characteristics, suppose if I am taking the practical characteristics like this, the low pass filter we are using to recover the original signal, the practical characteristics is monotonically decreasing and increasing. Okay, the higher frequency is not allowed. Now see, some part is overlapped here for the second one. We need only the original signal, but by using the practical low pass filter to recover the original signal for the condition of Fs is equal to 2 FM, there is a overlapping occurs here. So for the second case, we are using ideal low pass filter. Means exactly that, ideal low pass filter. So I will use another color, ideal low pass filter. Without any overlap is again occur, and here also. But in the previous case, see there is a gap is there. Got band. Even if you are using the low practical characteristics also, by using here there is a got band. It is not getting of the high frequencies. It is not getting the high frequencies here. It is not allows the high frequency. Whatever the within the range of minus 5 to 5 only, it is allows minus FM to the plus FM. even if you can use practical characteristics or the ideal characteristics here. But practical characteristics is very important here. But in this case, when fs is equal to 2fm, you have to use only the ideal characteristics. If you use the practical characteristics of the low pass filter, there is a high frequency also. There is some part of high frequency when you are using the practical characteristics. So to recover the original signal by using the condition fs is equal to 2fm, here ideal characteristics only we are using. Ideal low pass filter to get the original signal, because there is no any guard band in between of repeated signals. Okay, minus fm plus fm. Okay, my dear students, at n is equal to 0. That is the original signal is recovered by using the ideal low pass filter. Understood, my dear students? Now, the another case, it satisfies only the fs is greater than or equal to 2fm. Now, it is not recovered the original signal when the sampling frequency is less than the 2fm. Less than the 2fm. Let the 15 is the sampling frequency. I am taking the maximum frequency is a 5. It satisfies the greater than, the fs is greater than the 2 into 5 is the maximum frequency. We can take 10. Fs is equal to 10 we got, and the 15 is a greater than, and fs is equal to 10. Whenever if I am taking that is a up to that is equal to 2 into fs. If it is a less than means still it is a overlap. High frequency showing that is a low frequency, and the low frequency showing that is a high frequency. Okay, how it looks like I will explain here. The original signal like this. If suppose if I am taking the condition fs is less than the 2fm. So what is the fm? I am taking the 5. Fs is a 15. Now see the fs is less than the 2fm into 5. Fs is less than the 10. Less than the 10. So 0 here, it is a minus 5 and the plus is a plus 5, and here it is a minus 5. To recover here, the higher frequency shows is the lower frequency, and the lower frequency shows the higher frequency. So because this is a fm plus fm, and this one is a minus fm, but now it reduces, the fs is equal. It is not equal to 5. Suppose here the minus 5, 0, plus 5, and now it is less than the 10. Less than the 10. It overlaps the high frequency to the lower and the lower frequency to the higher. Even if you are using ideal low pass filter or practical low pass filter, even if you are using the practical low pass filter also, it is somewhat difficult because it is a overlap inside. There is a overlapping here. It will get the high frequency shows here the low frequency, and low frequency shows the high frequency. Means this line is high frequency and this line is a low frequency. High frequency is inside the low frequency and the low frequency is inside the high frequency. So it is not recovered by using either the low pass ideal characteristics or low pass practical characteristics. So fs is less than the 2fm. This effect is called aliasing effect. This effect is called aliasing effect. Actually, this point is a fs minus fm. Fs is a 15. minus 5, that is a 10. And this value is a minus Fs plus Fm. Actually, this is a Fm. If it is a 5, you can assume. Fs minus Fm. 5 here is a 10. 10 minus Fm here, the 5 inside it is getting the value. So we can't recover the original signal by this case. We can't recover the original signal by this case because when n is equal to 0, you will get the Fm. When n is equal to m1, Fs is plus or minus Fm. The frequency components present in this sample version, the frequency component in this sample version, Fm, Fs plus or minus Fm, 2Fs plus or minus Fm, and 3Fs plus or minus Fm. So x of t is a band limited to Fm having only the one component. Having only the one component only, my dear students. So as per the definition saying that it is recovered, completely recovered from its samples if the samples are taken at the rate of, if the samples is taken at the rate of Fs is greater than or equal to 2Fm only. Okay, it is not recovered when we can take as a Fs is less than the 2Fm, and this condition is called aliasing effect. So since here the overlapping occurs here. Okay, high frequency shows the low frequency and the low frequency shows the high frequency. Understood, my students? Up to this is a very, very important. All right. So any doubts? Okay. Thank you.